Now, fusion, on the other hand, is where you have two nuclei coming together to form a new element. And fusion is the most energetic of all nuclear reactions. It's the energy produced by the sun, and yeah, the fusion of these light elements are, become heavier elements, and yeah, and lots of energy is released. And so you can see the simulation here, and we have the fusion happening where we have the nuclei coming together and forming a heavier nucleus, and energy is released in that. And so that's what we're going to take a look at now. So again, fusion is the energy that is produced by the sun, and we're trying very hard to try to do this on Earth, to be able to control this, be able to get energy from it. It's very hard to control. You have to have extremely high temperatures, and up to this point, it takes more energy putting into the system than we actually get out of it. And so that's what we're dealing with right now. The nice thing is that you don't have the radioactive waste products. And so, with fission, we have krypton and barium, which are nasty, byproducts, and, continue to decay. And so we have to be very careful with those. We have to isolate those and take that nuclear waste and, make sure it's not going to be exposed to people. What's great with fusion, though, is that it, you don't have the hazardous waste products, and it's very safe. And you can shut it down very quickly as well. You just, if we were trying to control it, you just, don't add any more of the elements there, and then it shuts down. There's no chance for a nuclear meltdown like we have with fission. Now, it's very hard to make fusion happen because there's electrostatic repulsion. If you think about it, right, what you're trying to do is get these nuclei to come together, and they definitely don't want to come together. If you have, let's say, these two elements here, trying to come together, that electrostatic repulsion is extremely strong. And remember, the strong nuclear force only acts once they get, really close. And so to be able to get those together, you have to have very high temperatures and to make that happen. Now, once they do fuse together, they release a lot of energy. One of the, research and engineering projects going on is ITER, and you can look that up online. We also have research here in the U.S. with the ignition facility, and even private organizations like Lockheed Martin are trying to do this. It would revolutionize energy if we could, be able to, create a fusion reaction that's controlled and we could get energy from it. It would solve all our energy problems, no problem. It's just very, very hard to make that successful, but we're working hard to do that. So as we continue to look at the binding energy curve, we can look at it all the way on the far right-hand side here, where we have heavier elements, and those heavier elements will split and decay and so on. And so when a nucleus splits, and you can see this here, the products will have a higher binding energy. The nuclei will be smaller, the nucleon will be smaller, and therefore, the products, if you have uranium-235, it goes to 236, you have krypton and baryon, they're going to have a smaller nucleon number, and then if you notice, the energy curve goes up, and so the binding energy will go up, and energy is released in those reactions, and we've seen that with fission. Now, it's interesting, on the left-hand side with fusion, if you have lighter nuclei, and those fuse together, their products also have a higher binding energy. And so you can see on both sides of the curve where after the reaction, energy is released, and the higher binding energy afterwards is the effect there after fission and then fusion as well. Lockheed Martin has been working on compact fusion research and development, and there's an interesting video if you want to look that up on YouTube. I'm sure you could find that there about what they're trying to do. The National Ignition Facility is also working towards this, and this is in the US, and so you could check that out as well if you Google that. All right, so let's go ahead and take a look at here the combination here of deuterium and tritium, and we have two isotopes of helium combining together, and we want to find out the energy here. So what we'll do again, we'll get the mass difference of left side and the right side. The mass before, we can add up the deuterium and the tritium, and then the mass afterwards. And if you notice, the mass afterwards is smaller, right? And so mass is smaller. We can find the difference in mass, 0.018883 U, and convert it into kilograms, and we'll get our energy. And so that's the energy released in this fusion reaction, where the two nuclei come together, and then we're left with helium gas and nitrogen, or not nitrogen, a neutron. And so what's really nice is the byproducts are not hazardous, they're not radioactive, and it's a very clean reaction here. And here's our value in electron volts. So what do you notice what happens with binding energy as elements decay? We get the heavier elements over here, and they decay. Well, past nickel 62, every split on the right-hand side means the binding energy is stronger, and we can see that as we move from right to left on that graph. Now, on the left-hand side, what happens to stability when they fuse? Well, when they fuse, their stability goes up. As you can see that, the binding energy goes up. And so we see that as well. All right, so what's kind of interesting here, what's called the iron peak at the top. And I'll have you read through this if you want to pause the clip. This is some good information about, what kind of reactions take place based on the binding energy curve, which is really important conceptually here. So go ahead and pause the clip and read through this, and when you're ready to continue, you can hit play.